Hello, I'm Laura Lewis. In today's video, we're looking at nuclear fission and exam practice. So it's good that I'll be writing on the screen and explaining as I go what I'm doing. So it's good to write this down as we go along. Okay, so I've gathered some exam questions to look at today and to go through sort of live here. So obviously this is a recorded video, so you can pause and look back. Okay, but yeah, I'm going to go through it live. So let's have a look at the first question. So I've taken some particularly questions about nuclear power from exam papers. So for different exam boards. So this is fine for all exam boards. It's quite generic. Okay, so yeah, you need to know this for all exam boards. Okay, so let's have a look at this first question. So nuclear power stations generate about 14% of the world's electricity. So it's going up all the time. Okay, so at the time of publication, but this is going up all the time. Uranium-235 is used as a fuel in some nuclear reactors. Yeah, some nuclear reactors use it. Name one other substance used as a fuel in some nuclear reactors. So there is development of thorium reactions, but at the moment, another one would be plutonium. Okay, so let's just write that down. So it's like the planet, plutonium. Okay, they use something called a fast breeder reactor. You don't need to know what that means, but they're using other nuclear reactors, plutonium. Things like, yeah, thorium reactors are starting, but plutonium's used at the moment. Okay, so that's only 1 mark. So we'll look at the number of marks as to what you actually need to do. So 1 mark for 1 word. That's fine. Sometimes you might need to write a sentence for a mark, but it's not going to be a lot more than that. So always look at the marks there. That's where I've included them. Okay, we're going to go down a little bit. Okay, energy is released from nuclear fuels by the process of nuclear fission. So the fission is breaking apart of nuclei. Okay, fusion is bringing them together. So fission is a little bit, it's actually fission is named after the cell process. So when cells divide, it's called binary fission. And actually that was discovered before nuclear fission was. So nuclear fission is actually named secondary to cells. Okay, so you might have seen that word before in biology. It just means to split apart. That's all that means, that word. Okay, this energy is used to generate electricity. Describe how this energy is used to generate electricity. Do not explain the nuclear fission process. So for this one, this is why you sort of look at what is being asked. That you could go ahead and you could explain how nuclear fission works, but you won't get any marks. Because you could be scientifically correct, but if that's what the question is not what the question is asking, you won't actually get any marks for it. That's what I've seen some students do. Is that they write something which is correct in scientifically, but it's not what is being asked. Okay, so sometimes it's just because people are a bit worried and they don't read the question properly. And I've gone through it several times, I've misunderstood, but just read it again to make sure. So it says, the energy is used to generate electricity. So it's about generating electricity. Describe how this energy is used to generate electricity. Do not explain the nuclear fission process. Okay, so we don't need to talk about actually how it works. Okay, it's just that we've got energy to generate electricity and how that works. So I'm going to go on to a second slide here, so it's plain. And I'm going to draw a few things. A nuclear power station, it doesn't really vary that much from a conventional gas or a coal fire. So because we're not describing the process of fission at the moment, okay, that we're just going to draw the nuclear reactor as a box. Okay, and we can write nuclear reactor. Whereas later on, obviously, we could get a question we have to describe a bit more. Okay, so really, nuclear reactions, what we actually want from them is actually heat. Okay, so produce heat or thermal energy. Okay, thermal energy. So it's just good to sketch along with me. Okay, it's kind of printing up. Oh, no, it's not. Yeah, so you're not going to get marked down for a bad sketch. Yeah, it's not art. Okay, nuclear reactor. Sort of underline that a little bit. So the main purpose of a nuclear reactor is actually to heat water. Okay, so I'm going to close that off. I'm going to okay, so was going to seal that off. I'm going to sort of like seal that off here. Okay, and there's going to be water pumped around it. So this is water being pumped around. Okay, so I'm going to draw a pipe. Obviously people are going, yeah, it's a lot more complicated, but obviously for the purpose of this we don't need to describe nuclear reactions. Okay, so water is pumped around. Okay, it's pumped around nuclear reactor. Okay, but it's actually what they use. They actually just use water. Okay, so water's pumped. So let's. I'm going to just put the. Going to reroute the pipe here, only because to go around the writing. That's not it's not important. It's rerouted. You can just draw a straight line. Okay, so as it's pumped around the reactor, okay, there's lots of heat coming off. So I'm going to draw red lines for a minute, just for the purpose of illustration. Okay, so when water is heated, it gets hot. It also turns to steam. So water is heated and turns to steam. Okay. So water is heated and turns to steam, and this is under a lot of pressure. So under a lot of pressure. So if you've ever seen steam in a pipe, you know it's under pressure. Even if coming out of a kettle, it's under quite a lot of pressure, isn't it? So steam's actually a very dangerous thing because yeah, it's under lots of pressure, and obviously it's very hot, and steam burns worse than the water burns. So it's very dangerous to go anywhere near steam. Okay, so what are we going to do with this steam? We've produced the steam. So what we're actually going to do now is we're going to run it through what's known as a turbine. Okay, so a turbine is kind of like a big fan. Okay, let's have a turbine. Okay, so the steam comes here and makes a turbine go around. So the steam, so pressurized steam. Okay, pressurized steam turns a turbine. Okay, this by itself doesn't do anything, but it's what it's attached to. Okay, so it turns around very, very quickly. So I'm going to sort of draw arrows, it going round quickly. Okay, so a bit art class, isn't it? Okay, so what is actually around that is a generator. Okay, I'm drawing wire in here. Okay, wire. Okay, and in the middle of that is a big magnet. Some of you may obviously remember this and think, oh, okay, yeah, I can see where this is going. Okay, so that's the magnet is attached to that turbine. Okay, attached to this. So what happens here? Let's get a different colour so I can see it a bit better. So pressurized steam turns the turbine. So this in turn. I'm going to zoom out in a moment to make a bit more space. So it's going to zoom out. This in turn, here we go. This in turn turns a coil of wire. So generally the wire turns around the magnet, but you could have it the other way around, as long as there's relative motion between the wire and the magnet. Okay, so you've probably much done that in class called induction. Okay, in turn turns the coil of wire around the magnet. Okay, and what this does, okay, it's called induction. So this generates electricity. Okay, generates electricity. Okay, just for the completeness. Okay, I'm just going to draw some extra bits here. Okay, what happens to it afterwards? Okay, so we'll go and look at exactly what's needed by the question in a moment, but yeah, just for completeness for you to draw this, I don't want to sort of leave it hanging half done. So I'm just going to get do that for a moment. So when it actually comes out of the generator, it's actually very high current and low voltage when it comes out of the generator. But that's not really any good for transmitting electricity. Okay, so we need something called a transformer in here. Obviously, it's not to scale. Okay, it's just obviously where you can describe it. So, transformer. So, this actually is a step up transformer. Okay, step up. So, it increases voltage. So, this is another part of your physics syllabus is about transformers. So, you can get a bit of bonus content here. Increases voltage, decreases current. Okay, why do we need to do this? You're probably thinking. Because if electricity has a high voltage and a low current, it doesn't heat the wires up very much. A high current, so that means lots of electrons are going through the wire at once. That means the wire will heat up. And actually, what that would mean is that you lose a lot of energy by thermal energy loss when you transmit it, because the next process is to transmit this. So in the UK, we have pylons. Okay, so in the countryside a lot. Okay, it's to transmit electricity like that. It's going to zoom out again. The whole thing. So they transmit at a very high voltage. So they transmit. Oh, a bit of mess there, didn't I? Transmit. I can read that. Transmit at a high voltage. So when I say high voltage, it's about 132 kilovolts. Okay, yeah, that high, to prevent energy loss by heat. Because that's expensive for the company making it as well. And also would pass on a lot of expenses of people buying electricity, like for electricity bills. To prevent energy loss as heat. Okay, so yeah, just for completeness, we're going to draw a wire going down here, some wires going down here. So before it gets into homes and businesses, okay, we have another transformer, because we know we don't get that into our houses. We have a step down transformer before it goes to homes and businesses. Oh, I'll zoom out again. Okay, we have a step down transformer. So this time decreases voltage, increases current. So that's before it goes into our houses. Okay, so the thing after this will be into the line, literally. Okay, homes and businesses. Homes, businesses. Okay, right, so let's go back to the question. It's got plutonium still there. Okay, so energy, so describe about energy, so we can write this now in prose. Okay, so that means continuous writing. So let's start off. So the main purpose of a nuclear reactor. I mean, I'm going to go off the line a bit because I might quite big for everyone to see it, but obviously on yours you could write smaller. Of a nuclear reactor is to heat water. And turn it to steam. It to steam. Okay, the steam, as we saw, is under pressure, under high pressure. It turns a turbine. Okay, turbine. So this is attached to a generator. To a generator. The generator is a coil of wire that's spun around a magnet. Spun around a magnet. To generate electricity. Okay, 3 marks. So water is heated and turns to steam, 1 mark. It's actually a generator. Okay, so it's like steam. 1 mark is nuclear reactors heat water to steam. Next mark, the steam is under high pressure and turns a turbine. Number 3, this is attached to a generator. Generator is coil of wire spun around a magnet to generate electricity. Okay, we've actually completed the task given to us. Okay, so let's have a look at the next question. So yeah, now we've got the process of fission here. Okay, so usually we say don't describe fission. Fission is going to come up later. Okay, let's have a look. Trying to understand this then. Let's have a nice blue. We show green. So the diagram shows nuclear fission process for an atom of uranium-235. Okay, so that there, let's just try and remind ourselves what that means. Okay, 235 is the mass number. Okay. So uranium comes in 2 different types mainly. So uranium 235, that's how you say it. You say uranium, or it's a U, or uranium 235. You always say the name of it and then the number, like how I'm saying it. It also comes in uranium 238 in nature. Okay, they are different isotopes of each other. So isotopes. So that means they're the same number of protons different numbers of neutrons. Okay, so let's get to, obviously it's very important to understand that, what that word means. Different number of neutrons. That's what an isotope is. Okay, right, it says the diagram shows a nuclear fission process for an atom of uranium-235, so one of the isotopes of uranium. We use 235 because 238 doesn't split. It's what's called as not fissile uranium-238, so 235 is. So complete the diagram to show that how the fission process starts a chain reaction. So this is important because I've actually answered exactly the same question in class with students. Okay, about this. So neutron goes into uranium-235, and you have xenon 140 and strontium-94 being produced, and you have 2 neutrons. Okay, so what will happen there is these neutrons, it's actually very simple actually, will go on to split. So we're just going to write U235. Okay, we'll go on to split more uranium. So let's put another one down here. This is a chain reaction, so that means that more than one reaction is obviously happening. Okay, and then that uranium will split into the same components. Okay, neutrons. Okay, we'll write a little dot there, the neutron. Okay, Oh, so I forgot about the strontium there, didn't I? SR94. This one will do the same. Okay, xenon or xenon 140. You can write N for in short for neutron. That's the proper way of writing it, actually. SR94. And to get our full 2, that's 1 mark, and to get our full 2 marks is actually to do it again. I know it sounds funny, but I want to show that it happens again and again and again. Okay, so just another one will be okay. Okay, strong. You can see obviously that it increases. Xenon 140. So it's going to, and then this neutron and that neutron U235. More neutrons. Okay, so xenon 140. SR94. Try and get those out of the way. It comes in one slice. So you have to do it so you have to show that it's splitting more. It's splitting more and more. So it's increasing. It's ever increasing. Okay, how many it's splitting. So it's just a diagram you need to do here. 235. More neutrons. Xenon 140. Strontium 94. Okay, so you have to do it sort of twice. Okay. Oh, 235. And more neutrons come out of that. Let's just do it a bit neatly underneath. No, let's do something. Okay, so the main point of that, I'm going to draw it again sort of underneath there. Okay, so I'm going to draw a bit shorthand, saying a neutron, N for neutron, U235. Okay, and that goes on to split into 2. It's called daughter nuclei. Okay, so we had xenon 140. I'll make them go down here a bit more. SR, so strontium 94. I'm going to make the neutrons come out a bit further, make it easier to draw. Neutron, neutron, and those neutrons go on to split more uranium 235. Sort of drawing out again, really. Okay, and then those themselves produce. Okay. More neutrons. More strontium. That produces more xenon. More neutrons. And xenon 140. And then that splits one's a bit time consuming, isn't it? And then these neutrons again, just as sort of the last bit, go on to split more 235. That goes on to xenon 140, more neutrons, strontium 94. Okay, and then that one's U235. Okay, so xenon, just going to zoom out a bit. And 140. So this is coming from this one I'm trying to show you here. So then, yeah, it gets a bit crowded, doesn't it, on the page? Okay. Strontium 94. Okay, then these neutrons go and split, so that you have to show 2 stages of the process. Okay, to gain that 2 marks. It seems you're doing a lot, but once you get used to it, So 2 neutrons. So always have 2 neutrons coming from it as well as the actual elements. Strontium 94. And finally, we're getting there. This splits uranium 235. So strontium 94, neutron, zoom out, neutron, xenon. It doesn't really matter, xenon and strontium at the top. So what we see here, you have 1 uranium splitting 2, and that produces 4, and it goes as a square. So you go 2, 4, and obviously it spreads out. Okay, to form. You can tell here that each one's gonna have 2. So be it doesn't just double, it goes, and so it'd be 16 and so on. Okay, they want to show 2 stages like this. Okay, so 2 stages need to be seen. Okay, so I think that comes to the end of our video. We've overrun a little bit, but thank you for listening, and see you in another video. Goodbye.